Hello, everyone. Thank you for joining us today. It's my great pleasure to introduce a great friend of mine and a colleague, Dr. Xueying Yu, to join us and present in the colloquium today. Dr. Yu is a tenure track faculty member at the Atmospheric Science Research Center in University of Albany. She is an expert in the interactions between air pollution and greenhouse gases, and specifically on methane. So to quantify global methane budget using a variety of interesting tools from modeling, satellite data. So we overlapped for two years at Stanford while we were both postdoc here. And one thing I really admire Xueying's work is her work really touches on many different disciplines. Of course, methane is a topic that different disciplines are really interested in. So I'm sure everyone, no matter what your background is, will learn something from today's talk. So please join me to welcome Dr. Yu.
Hi everyone, my name is Xueying, and first I want to thank you for the opportunity to let me share my research with you, and thanks Minghao for hosting this visit, and thanks the SoMAS committee for making this visit happen. And today we are going to talk something about methane, in particular about the global methane budget, for what satellite isotopes and model can reveal. And in the beginning, just gotta click on, there you go, not too late. Yeah. Switch on. I can kind of hear it. No, I can't hear it. Okay. Yeah, you might maybe you can speak up a little bit more. Okay, I will go.
It's on.
Yeah, I will try to speak loud.
It's on. There's nothing wrong.
Oh, microphone.
Yeah, that's yeah, that's
The big one, the Zoom.
This one's the one that. Okay, maybe just
I think you just have to speak up.
Yes.
Talk
Good
to
job.
the room.
Okay, if anyone in the back couldn't hear me, you can just raise your hand, so I know I should speak up. Okay, in the beginning, I would like to acknowledge my co-authors for their contribution. And so, why would we care about methane? Methane is a very important link between carbon, climate, and chemistry. For example, shown here is effective radiative forcing from the IPCC AR6 report. What's shown here is how much can each tracers contribute to the global warming relative to the emissions, which means is the global warming that contributed by those tracers caused by the emissions since 1750. We can see that carbon dioxide made the largest contribution, followed by methane. However, methane is a little bit more complex than that because carbon dioxide is very stable in the atmosphere. So those global warming is caused by carbon dioxide itself. But for methane, it can react with other tracers in the atmosphere, generating ozone, and we'll see those can also be very important greenhouse gas. So the methane contribution here is not only including methane emissions after 1750, but also including the other greenhouse gases that are caused by those methane emissions. Together, methane emissions contribute to around 65% the radiative forcing of carbon dioxide, and is in play a very important climate chemistry interactions. Another thing about methane is it is an excellent target for carbon mitigation because methane has a very high global warming potential. 20 years, it is around 85 equivalent of carbon dioxide, which means if we have one more of methane in the atmosphere, and then also one more of carbon dioxide in the atmosphere, then at around the 20 years scale, the global warming contributed by those methane could be around 80 times of those contributed by those carbon dioxide. Well, in the meantime, methane has a very short lifetime, around 9 years, compared to the hundreds years of lifetime of carbon dioxide. So the strong global warming potential and the short lifetime makes methane to be an excellent target for the carbon mitigation. Methane is also a precursor of ozone. In the stratosphere, ozone can be very good, to block the radiation from the sun. But in the troposphere, ozone is an important air pollutant. As a precursor of ozone, this links methane with air quality. Finally, methane is an important field. So if we can collect those methane, have a smart use of them, those can be very important to the energy use. So it's also important things about methane. How methane looks like in the atmosphere. It's in fact showing a mystery. Shown here is 2,000 years of atmospheric methane concentration from ice core and the atmosphere. Today's methane level is around 3 times of its level in the pre-industrial time. If we zoom in into the recent decade, the methane increasing looks even more mysterious. Shown here in the zoom in panel is the global monthly mean methane from NOAA. It's first increasing and kind of stopped increasing, reached to a relatively steady state around 2000. And after 2006, methane continued the increasing trend. The reason behind this stable time period at around 2000 and the regrowth after 2006 is still remaining unclear. Well, for the most recent years, for the years after 2000, methane is showing a even more mysterious behavior because we all know at the year of 2020, we have been through COVID, so which is combined with a lot of industry lockdown. This is combined with the decrease of anthropogenic emissions. However, with those decreased anthropogenic emissions, the methane is showing an accelerated increase in the atmosphere. The reason behind this is still remaining explored by the recent studies. Some may attribute it to the atmospheric oxidation changes, because with the anthropogenic emission decrease of NOx, the atmospheric oxidation capability also decreased, which is a major methane sink. This causes the methane sharp increase. While other studies might attribute this sharp increase to interannual variability of wetland emissions. And this panel is showing a more close look of the red square. So how well do we understand the methane budget? Shown here is the global methane budget of 2010 to 2019 from the Global Carbon Project. It's listed two values. The first one is a bottom-up estimate. For example, emissions from bottom-up estimate come from how much methane is emitted per animal times the animal population. It can also from how much emission is emitted per facility based on their report. The second value is the top-down estimate, which is infer the methane sources and sinks based on the atmospheric concentration measurement. On a global scale, we can see the bottom-up and top-down estimate. They have a very large discrepancy. The total global emission has nearly 100 teragram per year discrepancy, and the largest discrepancy comes from wetland and fresh water. Other methane sources also include the fossil fuel, agriculture, biomass, and also other natural emissions. Well, the uncertainty in the methane is not only in the emissions, but also in the sink. The total sink discrepancy between bottom-up and top-down estimate are also around like 100 teragram per year. Interesting thing is if we combine those total emissions and total sinks to see the changes in atmospheric burden, then the bottom-up and top-down kind of have a better agreement. This indicated that inferring the methane sources and sink based on the atmospheric abundances is a low-post problem. However, what we can measure, the methane concentration in the atmosphere is actually reflecting the changes of atmospheric abundances. So in this talk, we are going to explore all those knowledge gaps that we just discussed. Why would those top-down and bottom-up estimate decrease? And are current approaches capable to address those existing knowledge gaps? And what is the role of the hydrology in the recent methane increase? I'm going to show it in 4 different cases. The first, we are going to using observing system simulation experiment to explore how well can current inverse analysis of high-resolution satellite data to resolve methane fluxes. Then we are going to apply the method that we diagnose the index OC to the real satellite data to look into the global methane budget. After that, we are going to move into the isotope, the carbon-13, and also the D to evaluate what are the processes behind the isotope signatures. Finally, I want to use a simple case of monsoon rainfall to discuss with you about the role of hydrology in the recent methane increases. So in the beginning, let's start with analysis to see what are the capability of satellite to infer the global methane sources. And this is credited to ESA and Saron. This is showing how tropospheric, which is a low Earth orbiting satellite, to do the measurement across the Earth. It provides around 7 kilometer pixel size with near daily overland coverage. And the methane concentration is inferred from both short-wave infrared and near-infrared. So the benefit of tropospheric, I would say the advantage of tropospheric, it is a first satellite to show the global full coverage of the methane concentration, which offers a very unprecedented opportunity to quantify methane emission variabilities and the underlying drivers. To evaluate its impact, a common way to do is using the observing system simulation experiment, the OSSI, which is commonly used to estimate the impact of proposed design of new satellite. The basic idea behind those OSSI is first, it will have a synthetic truth emission, and then also a prior estimate of those emissions or other state vectors that we want to test. Then we use chemical transport model to project those synthetic truth emission into the observations following the satellite sampling. Then we put those synthetic observation and the prior emission into the inverse system, which will generate an optimized solution. Then we compare the optimized solution with the synthetic truth to say if those optimized solution can effectively correct those prior biases. To be more details here in this OSSI, we are exploring the recent satellite tropospheric capabilities. Here is a more detailed configuration in our OSSI. We use different inventories as a synthetic truth and as a prior, then using JustCam version 11 to do the true emission simulation. Well, we use JustCam adjoint model, which relying on a different version of the forward model to optimize the fluxes. There are two focuses in this OSSI. The first is the methane emission spatial pattern. Because tropospheric is the first satellite to provide a nearly full coverage of methane concentration, so we want to test if these observations can effectively recover the spatial pattern of methane fluxes. The second focus of our OSSI is evaluating model transport error, which traditionally is really a major challenge in high-resolution inverse analysis. And to do for comparison, we also do another set of OSSI where we have accurate methane emission flux estimate in the prior for comparison, and also do not have the model transport errors for comparison. Let's see how the models works. Let's start with something clean. So shown here is initial gas minus true, which is the prior estimate minus the true. Those blue colors indicating that the prior inventory is underestimated compared with the true fluxes. Shown here in the red is the optimized minus true. It's showing how many errors can be removed by the inversion and the satellite data. This is the most clean cases where we have a spatial accurate prior, only have a domain weld emission bias, and no transport error in the model. So the model is very clean. We can see that the inversions can successfully improve emission estimate at 25 kilometer scale, which is the resolution of this model. And the labels in this panel, the BELS is the domain weld emission BELS reduction. R is the spatial correlation of the optimized solution to the true fluxes. However, when we add a little bit not that optimal scenarios, when we use a spatial inaccurate prior in those inversions, we found that the picture changed a little bit. The solution degrade a little bit. However, it can still effectively remove the domain weld spatial bias, but the missing sources has been misalligned to large nearby sources. For example, in the south of the Hudson Basin, where the emission is missing in the initial gases, instead of scaling those emissions up, the inversion tend to allocate a false emission in the upwind of those sources to compensate for the downwind concentration mismatch. Well, those are with the clean model, no transport error. But in the reality, the transport error is always be here. So what will it looks like when we have the transport error? When we have transport error but the spatial accurate prior, we found the model tend to overcorrect the large sources to compensate for those transport error. But when we have both transport error and the spatial inaccurate prior, a very sad thing happens. The current model tend to have only mineral belts improvement over the prior. This indicated a very important knowledge gap that even with all those advances in satellite observation, the current model actually cannot have a very good use of those information from satellite. It combined with the transport error and also the spatial inaccurate prior, it only improves the mineral belts improvement. So we need so there is really a strong need to improve the model to have a better leverage of those satellite information, which is as we do later in our study, we use alternative inverse method to overcome those limited. Because one thing that abandoned us to achieve a better estimate is behind the scaling factor approaches. If emission is only scaling down or scaling up, and then it will have dependency to the magnitude of the prior emission. So here we design alternative inversion method to try to remove this dependency. And if you're interested in more details, about the technique, please reach to me afterward. And we also design a new spatial downscaling approach to infer emission at 0.1 degree. Because another beautiful thing about satellite is it offers a very high spatial resolution of the observation concentrations. But a lot of current global model is limited by the computation speed that for on global estimate, it's very hard to infer emission at a comparable resolution of satellite. So here we design a new spatial downscaling approach, combine both troponin oversampling and also the prior emission estimate to project the emission into 0.1 degree. Our new approaches tend to be a very good model performances. Shown here is evaluating the downscaling approach using 1 month of Aussie over the North American. When we have the clean model without the transport error, we found that the downscaling and also the alternative scaling factor approaches have comparable performance with the fine-grade adjoint model, which is using traditional 4D VR data simulation approaches. However, when we have transport error in these model simulations, as we have seen before, the fine-grade agent model tend to have limited ability to reduce the domain weld bias reduction. But this spatial downscaling coupled with alternative inverse strategies can successfully reduce those emission biases. It also has another benefit of mitigating the transport error and also reducing the computational cost, because the spatial downscaling offers a very fast speed. It's like can infer the emission at 0.1 degree on a global scale in like 2 or 3 weeks. But the traditional method computing at the 0.1 degree might require converge like 100 years based on the test that we do. So from the first test, the first Aussie is from the first Aussie, we built a new inversion frameworks to have a better leverage of the satellite information. And next, we are going to apply this method into the real satellite data. To apply it for the 2 years of troponin satellite data to see the global methane emissions in the real world. Shown here is the troponin methane oversamples averaged across 2018 to 2021, averaged into 0.1 degrees. We see that the troponin methane concentration really reveals some very important source signatures for methane. You can see a clear spatial enhancement of methane concentration enhancement, such as in California near Mississippi River. Also, those spatial patterns in the Middle East might related with fossil fuel exploration. And what cannot be ignored is a very sharp emission concentration enhancement over the East Asia. So now let's move into the real data to see what the inverse analysis can tell us from those methane observations. But before that, I want to go back a little bit to a refresh of the methane processes. The methane is not only driven by the emissions, but also driven by the methane sink. The major sink is methane reaction with OH. Our inversion has two treatments of OH. One is using the simulated OH as a fixed constraint, which means it's using the modeled OH consistently in the inversion. Another is optimizing both OH and emission simultaneously in the inversion. It will have a higher degree of freedom. So the inversion is more flexible to trace the progresses behind the methane concentration changes into either emission or OH, but it may face an overfit problem. It might face a Leo-posted problem. This is very important because next you are going to see some interesting happen in our inversion. When we use this Analyses that will develop the test inversion framework in the Analyses into the real world, the inversion converge at two different solutions of the global methane budget. All those fixed OH tend to converge at a higher global methane fluxes, while all those optimized OH tend to converge at a lower global methane fluxes. Shown here, X is the global methane emissions, Y is the global methane sink. And the orange color indicated the prior probability of the emission estimating the inventories. And each dot indicated one inversion solution where we vary the assumptions of the prior OH assumption or vary the inversion strategies to have an ensemble of the inversion. Those fixed OH tend to be around like 80 or maybe 60 teragram per year higher of those optimized OH inversion. So the next question is, why would that happen? So which solution is real? And to evaluate that, we're relying on other tracers for the airborne measurement of OH and CO. The reason we use CO measurement here is because the major sink of CO is also OH. And it turns out that those aircraft measurements tend to support the fixed OH solution. And this indicating that optimizing methane sources and sinks simultaneously in the optimized OH tend to be a Leo-post problem because the inversion is relying on the concentrations. Concentration is really reflecting the net mass changes of methane in the atmosphere. And even with the dense troposphere data coverage, it is still a Leo-post problem. But the good thing is the fixed OH tend to agree very well with the airborne OH and CO, so it can still reveal us some information about the global methane budget. Shown here is the optimized global methane sources of the fixed OH. Wetland is the largest sources, contributed to around 29% of the global methane sources. Right here in the right, on the top is the optimized global methane emissions. And in the bottom is the emission correction compared to current bottom-up inventories as listed here. We found the emissions are overestimated in the North Hemisphere high latitude region, but are underestimated in the tropical and subtropical regions. Furthermore, from these regional global methane emissions, we can further infer in the underestimated hotspot because the spatial downscaling approach that we have just tested in the OC can infer the emissions as 0.1 degree, which is around the 10 kilometer scale. This gave us a very important opportunity to look into the emission hotspots on a global scale. Shown here in the left is the emission increases in the past decade, inferred from Edgar bottom-up estimated. The colors indicated how much emission increase magnitude is from the bottom-up inventory. Well, shown here in the red is the hotspot emission correction from the fixed OH. We found that the Middle East and the East Asia tend to be a very important region. In the Middle East, emission has been sharply increased in the past decade, will also be underestimated in current inventories, which might relate with all those fast developing fossil fuel explorations. But in the East Asia, it tends to be a little bit more complicated because in the East Asia, the emission correction tend to have a seasonal dependency, which we will explore later. In the last session, we found it tend to be hydrology related. And showing here is just to have a global overview of how those emission hotspots looks like. And one important thing I want to point it out is we still have a Leo-post between emissions and sinks, but the emission hotspot inferred here is very valid because it's clearly stand out from the background. Next, back to, I know we have seen this before, but I want to point it to another wonderful thing about satellite, because it's not only have a very powerful observation of methane, it can also have a very powerful observation about other tracers, which opens a window to look into the methane oxidation chain that can help us to solve the Leopold's problems. For example, it's shown here is also have observation of formaldehyde and CO. So to further solve these Leopold's problems, we not only simulated methane, now we are simulating the methane oxidation chain to include both methane, formaldehyde, and CO. We also put methane chloroform here, which is a classical tracer or proxy to infer the OH concentrations. In the atmosphere, based on the current model simulations, around 96% of carbon in the methane will be oxidated into formaldehyde, and nearly 100 of the carbon in the formaldehyde will turn into CO in the atmosphere. So by implementing those multiple tracers in the oxidation, it opens a door to look into the methane oxidation processes in this way to solve the Leopold's problems between the emission sources and the sink. Shown here is the optimized OH from the inversion. Alpha here is infer the inversion that we use all of those tracers. We found a very interesting thing is the optimized OH tend to be lower than the prior, especially in the tropical regions. So with those lower OH, it's indicating a potential lower methane sink. With that, now let's look into how the methane global budgets might change after we have implemented those methane oxidation processes. A good news is the emission estimate tend to be lower than the fixed OH solutions. So which means that maybe we did not emit it as much as those previous fixed OH inversions suggested. Shown here in this plot, X is the global methane emissions, Y is the tropospheric global methane sink, and the outer color indicated in the very top right is the OH inferred from methane chloroform, which is commonly used as a traditional proxy of OH. Also, a gray well with also has been used to evaluate the current models. And compared to this point, the plus signal, which is the solution inferred from the methane oxidation solutions, it tend to have a lower global methane emissions. But we still want to point it to information is compared with the inventory, as shown here as a very large dotted green dot. The emission inferred from the methane oxidation solution is still higher than the inventory suggested, which means current estimate in the inventory is still underestimating the emissions that we emitted. So shown here is for the take-home message from satellite, we have we improved the model frameworks and identifying the emission hotspots, and also design some new frameworks to rely on the methane oxidation to infer both the atmospheric oxidation capabilities and also the global methane sink, methane sources to solve the Leopold's problems. Next, let's move to the isotope. Isotope seems to be a very different stories than methane. So what can isotope tell us? I know some people in this department also study isotopes, so I'm very humble to explain this slide. So just for those who don't know isotope that much. So isotope is actually reflecting a ratio in the atmosphere. Shown here in this equation, the R sample is actually the ratio of isotopes such as the carbon-13 of methane to the carbon-12 of methane. And the isotope signature replying to the R of the sample relative to this ratio in a reference materials. So it's different than looking at the methane concentration. The methane concentration can also be converted into a methane mass. It's like an absolute value of the mass changes in the unit of kilogram. But for the isotope changes, it's more reflecting the ratio of isotope to the non-isotope in the atmosphere. It's determined by the two processes, as shown here in the left. It's a source signature of methane from the Sherwood. Methane from different sources tend to have different isotope signatures. For example, the biomass burning tend to emit more heavy isotope than fossil fuel and than microbeam activities. If we only look into the mix of those different isotope signatures from methane sources, we can arrive at the atmosphere isotope signature before the fractionation as pointed by the red. However, what is even more complex is isotope also has different behaviors than the non-isotope in terms of the methane sink. The heavier isotope tend to react slower with the OH and also with other oxidants. So the measured atmosphere is tend to have a different than the atmosphere before the fractionation. So short story, the isotope can tell us of the emission and sink processes behind those concentration measurement. During the past decade, we have seen a decrease of methane carbon isotope in the atmosphere. It's like combined with the methane sharp increase in the atmosphere, the carbon isotope actually tend to be falling. This suggests an increasing role of biogenic methane sources because they tend to have a lighter emission source signatures, such as from wetland, freshwater, livestock, and rise and wastewater. So next we are going to do is we are going to put those isotope concentration, isotope ratio into the inversions to say what can inversion interpret of those isotope measurements. To do that, we use a new set of data simulation framework. Shown here is an ensemble that we use different simulated tracers to say how different isotopes tells about the story. And before we move into the solution, I want to use this slide to further explain what isotope can contribute to this inversion. First, shown here is a spatial and temporal correlation between different emission sectors in terms of the emission correction identified by the inversion. If the inversion cannot have a well separation of those emission sectors, they will have a very strong correlation because inversion just tend to increase everything together. As shown here in the satellite, it's showing a very heavy correlation between anthropogenic sectors. However, when we have isotope information into this inversion, we found this correlation has been decreased. This indicated the isotope, the way that isotope contribute to the inversion is to have a better separation across emission sectors. And when we put the isotope into the inversion, we found something also very interesting happened. Shown here in this table is the total global methane emissions and also the anthropogenic emissions, natural emissions from the prior estimate optimize the solution and the isotope informed optimize the solutions. We also aggregated to different regions as shown here in the map. At a global scale, after we include those isotope concentration ratio into the inversion, we found the global methane budget tend to increase by around 20 teragram per year. However, even though it is increased by around 20 teragram per year, it is still a very minimal improvement compared with the 100 teragram per year discrepancy between the bottom-up and top-down estimate. But what is very interesting thing is all those 20 teragram per year emission increases that identified by the isotope is tend to be located in the East Asia, as shown here indicated by the yellow color. So what isotope did do in this inversion is to draw our attention into the region, in particular to the East Asia. And it's also attributed all of those East Asia emissions into anthropogenic sources. But for the wetland, for the natural emissions, we found less wetland or freshwater emissions when we include the isotope. However, compared with the prior estimate, it still reveals a much higher emission estimate compared with the inventory. So as a take-home message, after we have isotope into our model framework, we found that the isotope indicated an underestimate of anthropogenic emissions, in particular in the East Asia. But still, because the isotope is decreasing in the recent decade, so it's revealed an increasing role of biogenic sources in the recent decade. Finally, I want to share with you is from the previous, we have seen a lot of drivers might influence the methane emissions. But one very interesting thing we have wondering is what is the role of hydrology in the recent methane increases? And I want to use a very And I want to use the eastern monsoon cases that we identified as really a very interesting special case here. And for those of you may not very know monsoon well, monsoon is like based on the contrast between land and ocean to have different atmosphere circulation patterns between spring, summer, and also winter. So it will result into different rainfall patterns between different seasons. And in our inversion, we found that the methane emission increases in the South Asia tend to be coincided with monsoon. Shown here is the emission correction, the optimized emission minus the prior emissions of different months from May 2018 to October 2019. What's labeled in the title is the total emission corrections, the emission increases identified by the inversion on a regional scale. We found that it has a different, very distinguished different behavior between monsoon season and non-monsoon season. For the non-monsoon season, the emission tend to be well concentrated in the inventories. But for the monsoon season, it's identified a very sharp emission increases. For example, during the July, we can see the emission increase strongly over Bangladesh in July following the monsoon onset. But in October, the emission tend to be diminished and shift eastward in October following the monsoon withdrawal. Across the entire monsoon season, there are around 10 to 13 teragram methane emission increases during the monsoon season. And I want to hypothesize one potential driver that behind this is the role of hydrology. When monsoon is arrived in this region, it tends to have a higher rainfall. So this will increase the water body in the land surface, will increase the wetland extent, increase the wetland emissions, also increase the wastewater, increase more biogenic emissions from wastewater and rise on also biogenic sources. So with that, I want to conclude my talk. So we look into the global methane budget, in particular to look into what satellite, isotope, and model can reveal. We first using observing system simulation experiment to evaluate our advanced current model to have a better real rate of satellite data. And then from the real satellite measurements, we real the emission hotspot and infer the atmospheric oxidation capabilities, combining multiple tracers. Finally, we use isotope to see what are the underlying processes of anthropogenic and also nature global methane sources. We found that the isotope has drawn our attention into an underestimated anthropogenic emissions, particularly in the East Asia. And finally, from all those analyses, we found a very interesting special case related with monsoon rainfall, which indicates that hydrology indeed playing a role in the recent methane increases. With that, I would like to thank you for your attention, and I'm happy to take any questions.
Thank you so much. We have 3 students that might ask the first 3 questions. So Jules, Jared, and Donkey. Go for it, Donkey.
First of all, thank you for your presentation. And my question is about more general things about the methane emission and the methane budget. As you know, for carbon dioxide, we have a kind of carbon capture and storage technology or carbon sequestration strategy for using the biological pumps like seaweed farming.
Yeah.
Is there a similar way to capture the methanes and store the methanes for not to emit the methane to the atmosphere?
Yeah, there are a lot of ways to currently and there are current studies to explore to remove methane from atmosphere, and it has different strategies for different concentration level of methane. For example, in a large scale, it might increase the methane oxidation capabilities. I know there are some I know there are some studies to try to build a carbon tree, like a tree, but with some filter outside of it to increase the atmospheric oxidation capability. So when the air is blown into this train, methane will be oxidized within it. This is like one strategy to remove atmospheric methane, or like removing the background methane. Also, there are also some technologies to capture methane emission, which is targeted for the emission hotspot. For example, from the wastewater, because microbeam activities tend to have can have the capability to generate a very sharp spike of methane concentration, methane emissions. Then there are also some techniques to capture those methane emissions. And another very interesting thing is those captured methane can later on be used as the energy to use as the fuel to provide, the electricity or other energy use. I hope this can answer your question.
Okay.
So thank you for your talk. I thought it was very informative and learned a lot. My question was about whether you are currently aware of any models that either top down, bottom up, or a combination of both that incorporate predictions of methane release from thawing from across.
That was my question.
Please repeat the last word, methane emission from the.
Just, I'm wondering whether any models that currently exist that can predict the accelerated rate of methane release thawing from across.
Sorry, forest. Yeah, I know. I think the several models I know. First, you can use the land process-based model to explore the carbon processes in the permafrost, because we all know that there are a lot of carbon storage in the permafrost. Once it's been melted following the global warming, then it has the potential to release a lot of methane in the atmosphere. I think current observation tend to have not reached to that area yet. So it's still the model to test the future scenarios. What happens if the temperature will increase? Based on my knowledge, it's basically probably mostly from the process-based model. Also, there are some machine learning-based model to try to develop a relationship between the temperature increase and also the response of the permafrost environment.
Hi. Great talk. It went a little over my head, but I still have a question for you nonetheless.
Yeah.
So you identified that models need to keep pace with the new satellite techniques.
Yeah.
Are you or your team, like, what are you working on in that regard right now, like for future work?
Sure. Oh, actually, those are very new studies that we either just submitted or published within 1 or 2 years. So one way is we try to identify new technologies to have a better identification of methane sources, because as we just see from the OC, the current model tend to have a limited, I would say, just still need to be improved the capability to capture those methane sources. For those methane sources, it refers to the sources that we do not know in advance. We completely do not know methane in the inventory, and the atmospheric inversion might attribute those sources into the upwind sources to compensate for the downwind concentration mismatch. So one approach our group is to revise the inversion strategy to remove those methane sources. And another thing we are going to is for the atmospheric oxidation capabilities, because it's a little pose the problem to infer both methane emission and sink from the concentration. So we are trying to develop the new technologies to bring into more constraints to separate the methane sources and sinks. And the third thing, as you hear, is the isotope effort we are doing. We want to interpret what information can the isotope to tell us about the methane budget.
Thank you.
And also, our group also has some new progresses about the machine learning-based approaches to use machine learning to reveal the nonlinear relationship behind those methane processes.
How significant is natural gas storage and transmission systems, leakage from those significant to the source?
I mean, the oil and gas emissions inside of the global methane budget. Yes, I want to use one figure in my introduction because now this is from the global methane budget. The fossil fuel production and use is around 120 terawatt per year. And so this is how much based on our current knowledge to contribute to the global total budget. Yeah. And the very interesting thing is because we know the location of the fossil fuel production and use very well, so we tend to have less risk of the reviewing methane sources issue in the top-down problem, which you can see here. It will agree very well between the bottom-up estimate and the top-down estimate.
Great talk. So most of the work I do is looking at links between environmental hazards and health effects. And we do look at things like, for example, like formaldehyde or something like that. Most of the hazard data that we use in our group is modeled based on some sort of fate and transport across a landscape, and you know, you end up with like you know, guesses about like what the hazard was at a certain spot based on someone's hospitalization record or something like that. And we're always looking for ways to, you know, better describe what a landscape's hazard might be. And it occurred to me that the granularity of the satellite data at 10K M is a lot bigger than what we are typically used to. But have you seen projects where satellite data is linked to like hospitalization records or something like a health endpoint? Because that's one of the, you know, bottlenecks we face is, you know, really trying to describe environmental hazards at the landscape scale.
Yeah, that's a very interesting question. Because I want to do the research into this area, so lack of the knowledge if the current literature was working on that. But I feel it's really a very interesting question, you know, for those landscape health issue and how it's compared with nearly full spatial coverage of satellite data.
Yeah. I mean, we're working usually at like 800 meter or something, so much different. But I wonder if there's a way to, you know, build hierarchy into the models or something like that with like another source of a chemical specific thing. So maybe I'll talk to you a little more about,
Yeah.
you know, it's a bit exploratory, but yeah. Daniel?
Yeah, thank you for the nice talk. That's an impressive amount of work.
Yeah.
I have a question to the OH. Clearly the OH is crucial to get the sync
Yes.
method right. And you had a slide where you said the fixed OH assumption is maybe the best, and you refer to the atom campaign. Then you showed two other data points where you optimized 1 and 10%, and you had much smaller sinks and sources. Your inverse model, and I wanted to understand, what does this 1 and 10% mean? Did you vary the OH concentration? And my follow-up question to that is, in your model, do you account for OH variation in concentration with height, for example? If it's cloudy at night, the upper troposphere OH is maybe greater concentration than at the surface. So that would be my follow-up question, but I did not understand. I saw the fixed OH, I understood that, but 1 and 10% optimization, it's scaled differently than I thought, and maybe I misunderstood that.
Okay, about the 10%, it's actually the model setting that we do to do the inversion. We estimated the prior error estimate of OH as 10% based on the range of OH. It does not equal to, it is not the range that the inversion can adjust. It just, actually, let me see if I have, because I did not put the details of the technique of inversion here. And what we do is the inversion tend to combine both the prior information and weighted by the prior error, and also with the observation information weighted by the observation error. And this 10% is used to describe the prior error. And we also vary this estimate from 1% or 10%, actually 10% or maybe like 20% to say how this error can cause sensitivity to our solutions. This is the 10% estimate. And for the second question, how do we account for the environmental maybe factors in the OH? For the fixed OH, it is simulated by current full chemistry simulation models. So it will account for the temperature, you know, for the other tracers concentration, just to give us an estimate of the spatial pattern and also the spatial variability of OH. And for the fixed OH, inversion is used this OH, and optimize is based on this fixed OH. We further optimize the OH and based on the observation concentrations.
Okay, I thought so. You have to run a whole other global model to get just that number right, to put it in your model. So therefore, it's quite impressive. Thank you.
I have a question about, you don't have a lot of time to go into the detail, but for the final case study, which I saw is really interesting, I guess, can you tell a little more about like what other analysis you are doing to make sure that this seasonal pattern is tied to the monsoon, and what else can you learn like about the specific detailed mechanisms?
Detailed mechanisms, okay. So about the monsoon part, isn't it a very interesting study? Shown here is the emission enhancement. So we also do like a spatial correlation, maybe like a culture-driven analysis to say how the emission enhancement identified here may vary with hydrology factors such as runoff and rainfall. So it has another figure, not in my slides, but in the published papers. It's showing two very it shows both the spatial correlation with temperature and also the spatial correlation with rainfall to identify what has a hydrothermal or the hydrology influence in the emission enhancement here.
Right, so these, sorry, just so I'm clear, these are modeled data?
Yeah, those are the emission enhancement identified by the version, which is the optimized emission minus the prior emission. The emission increases that is missing, currently missing in the 1-3. And we found those missing have a very strong spatial, actually seasonal pattern of the emission actually missing it in the monsoon season. And in particular, if we look into this figure, you can say it started in July, where July is following the monsoon onset. And then it started with underestimated around 70 GDP per day emissions, and then increase a little bit following the monsoon, become more intensive. And then in September, become mostly intensive. And then in October, the emission tend to be diminished following the monsoon offset withdrawal.
Sorry, just to follow up with this, and this is my ignorance about this, but how can you be sure that this is something related to the emission source? Like, could it be that monsoon also influence the sink process or those kind of stuff? I mean, I just don't know anything about this.
That's a very interesting hypothesis, because guess we haven't looked into it yet. So maybe monsoon changes the environment a little bit, maybe change the atmospheric oxidation capability, but it would be worth to investigate to it.
Very, thank you. Thanks so much.